So first off, Brooke and I would like to thank Cynthia for inviting us here and attending your GIS days. It's very exciting. So Cynthia asked us to present on applications of point cloud technology. I know you've seen dams and contours and other surface models here, but we've been asked to discuss on actually point cloud technology and how these data sets are defined and developed for work that we've done at KGS Group. So today our presentations are going to give you a bit of an introduction of what point clouds are. We're going to tell you how we define them, and then we're going to provide you some project examples and some case studies. So first off, so a little bit of a background from us. So KGS is a multidisciplinary company, and we have 400 employees. So the GIS department has 16 full-time people, and department manager and Brook Irving is one of our GIS technologists that utilize the point technology the most. So first off, what is a point cloud? Well, as we see in some other applications, a point cloud is essentially a mass points of X and Y data of a given coordinate system, and it has a value, and in today's context that value will be an elevation. There are some secondary values that value can mean, which I'll get into. The file size of the point clouds is what's the greatest power of them. They can be ranging in sizes of 200,000 to upwards of 100 plus or 500 plus points of size, which we've used. So the secondary values, as you've seen, is they can be RGB, which is the red, green, blue, which is the color of the imagery taken at the time of the imagery, or secondary after, and it's colored at that point of X, Y. The intensity, which is the strength of the signal in return, and as well it can also have other values, such as you can apply thermal to it and have any other value associated with that point cloud data. The beauty about point cloud data is it's becoming more and more adopted, and the data files can be exchanged much more readily in most software platforms. And those are just a sample of some of the point clouds. So first off, how are they used? So primarily they're used to develop spatial data sets, and they're great at capturing condition of objects and record what that object looks like at that exact point in time. And that's essential for how we use point clouds, and I'll get into those details as well as Brooks has some information, because she'll be speaking shortly. Why are they important? Well, they can quickly and effectively capture a project area for assessment, analysis, modeling, and they become very powerful to readily collect large areas or small areas inside 3D scanning, inside tunnels, and other applications where you just can't put people. So I'll give you a bit of background on where we obtain our point cloud data. So we've talked a lot about LiDAR data, and there was another presentation earlier about drone, and I'll talk to him. But we kind of break them out into two broad categories. This is an active sensor, and what an active sensor basically is, it's the sensor emits and retrieves that energy source. So LiDAR is a classic example, and platforms such as fixed wing, helicopter, drones, they're all LiDAR platforms. Terrestrial LiDAR, so 3D scanning, mobile mapping. If you're not familiar with mobile mapping, what you'll see is it's a LiDAR mounted on a vehicle, like a boat, ATV, a vehicle, and it's driven down lineal projects, and it does imagery and collects point clouds as it's going down that project. And 3D scanning is something we have as well, which is a stationary LiDAR on a tripod. It spins in a 360, and you can collect millions of points a second. So other sources of point cloud data, a little less accurate, but still valuable, and we still use them in various studies, which is radar And also another emerging field is underwater scanners, and we've used this data as well. The underwater scanner is, again, it uses sonar, emits a beam, pulse beam, and you can scan underwater. So that data is becoming, we've used that several times now, and it's become very valuable. So second is a passive sensor. So basically a passive sensor is a sensor that collects energy emitted from another source, i.e. a camera is a typical one. So in the earlier presentation with the Pinawa Dam, that's a passive scanner, and through auto triangulation, point clouds can be obtained. So photogrammetric stereo pairs, like Daniel had mentioned, historic imagery can be used to develop a condition in 1945 if you had stereo pairs, and you could analyze changes over time to a new LiDAR data set. So those are good applications. So typical ones that we obtain point clouds are from imagery, drones, as well as satellites. You can get point clouds from satellite. So I'm going to hand over to Brooks, where she's going to talk a bit more now that we've covered some of the fundamentals.
So I'm going to talk a little bit about matching project needs up with the technology you'd want to select when generating or gathering point cloud data. So the first thing to consider is the size of your project area. Is it a localized site? Are you looking to collect survey data perhaps just on a building, or is it a large site? Daniel had touched on this as well. So you have to kind of determine, is it appropriate to use more of an airborne capture or a terrestrial capture? Do you want to use a 3D scan because it's a building, a small site, or do you want to fly LiDAR because it's a remote site, heavily vegetated? It also ties in with your accuracy specifications. If you're moving towards a mapping reconnaissance, or is it going to be more of a detailed design right down to monitoring, which would require sub-centimeter accuracy. So you need to kind of identify that within your project. The site accessibility, vegetation of the site also kind of will drive what sort of technology you would choose to generate your point cloud. If it's like not very accessible, only by air or boat, automatically that changes the accessibility. But vegetation can also drive it. You wouldn't be able to use a drone, well, like a non-LiDAR drone, so one that's just using auto triangulation for a heavily vegetated site, because it wouldn't necessarily penetrate the canopy to get a ground if you're looking to produce a bare earth dam. As well, you need to consider your design and modeling requirements. For example, if you're doing a detailed design of modeling a pump in an existing structure, how detailed do you need it to be? Do you need to have a scan data that's going to get it down so you can see basically the nuts and bolts of the structure, or is it a wider scope so that you don't need that millimeter accuracy? And finally, what sort of integration ultimately is required for your project? Let's say you're building a bare earth dam of let's say a channel, for example. You might need to also capture bathymetry in addition to, say, LiDAR or UAV in order to produce that. So you'd want to consider what sort of things you would need to integrate in the future. So point clouds are being used across many disciplines. You can see up there, there's, it's across many fields. It's not just one. For example, geotechnical might be using point clouds to do slope stability analysis, and water resources might be using it to do a dam breach analysis. So some of the derivative products that you would get that you would be able to generate from your point cloud data. One of the common ones that we use is generating a digital elevation model from this. So this would include getting a surface model from the dam, then generating contours, and also doing various types of analysis using this dam. That could be slope and aspect, could be a line of sight analysis, all sorts of different things. You can also We also do a lot of 3D modeling and design from the point clouds. So those would be piping and structure models, like an existing, putting in piping into an existing building. That's where you would integrate 3D modeling with a point cloud data set. And earthwork models, you could use a 3D point cloud to get a modeled surface of the roadway. And from point clouds, you can actually do a lot of analysis with the point clouds themselves. So these could include asset capture, which could be anything from a dam structure to your hydro poles, hydrants, basically any sort of thing that you would want to, capture and manage. And then this would allow you to also assess the condition of the assets that you're capturing. And then if you were able to, acquire multiple point clouds over time, whether through LiDAR or UAV captures or 3D scans, you could then ultimately do a change detection assessment on your assets, so you can see how they're changing over time. And especially in Manitoba, it's of concern is the flood mitigation. So point clouds can be used during a flood event to analyze the flood as it's happening, and also to be used for preventative measures in the future. And it's also great because it provides a historical, basically, time shot of the flood as it happened at that exact time. And I'm going to pass it back over to Mark.
So we didn't realize there was going to be a mic, so when we practice this is a very seamless thing. It seems to be less so hopefully it's not breaking things down here. So what we wanted to get through some of these basics and then get to what I think everyone might be interested in is some applications and some demonstrations of how we've used point cloud technology in our company. So I'm going to just launch a bit of a quick video here, and I'll make it brief. How am I doing for time? We're doing okay. So this is an example of point cloud integration fundamentally. So this is a project we did where an existing structure and facility needed to be expanded upon. So it included additional structures, additional parking, additional piping, and all the other related engineering work that's related on it. So we, through a combination of LiDAR, imagery, 3D scanning, conventional surveying, we converted this point cloud data to a 3D model, a solid object model. Oh, sorry. Thanks, Brook. Yeah, there it is. Too tall here. Yeah, sorry. So it's a little video of a fly-through of the final design that was completed on a project. So again, this is so everything you see in real color comes from the point cloud. Everything in blue was modeled and designed in real space, and is an actual solid model for doing engineering drawing takeoffs, providing the contractors for cost estimating, presenting to the client for from the board of directors down, so everyone can see what the site looked like. So the benefits of this was we've taken the air photo, have draped it across the ground, and combined the expanded design. So all this parking lot here was proposed, all the site drainage on site, make sure there was no standing water and ponding would occur, and how well it integrated into the existing site. And then we do a fly around, and you can see that all of this is actual solid models. So everything in here can be dimensioned, and both horizontal and vertical, derived geodetic elevations, and as well as this allowed for a collaborative method for adjusting the design. So if they didn't quite like this, we could move the building around, so we could quickly do this. So not only is it a model outside, but we've also taken to the point of everything was modeled even inside the building, where all the electrical conduits and where all the structural piles and everything would fall. So I'll pause it there. I think everyone gets the idea. It's just going to go through doors and that. So, but that's one example of how we've taken 3D point clouds and darn it. This is a newer version than what I'm used to, so oops. I'm going to talk about another project here. So this is another example of just kind of keep it on the structural side of things just to see. So this is another example where point clouds have become a valuable tool for, again, 3D modeling and doing very precise models. So in the upper left is an actual 3D scan of an interior building with the structures. And again, a lot of this was done inside the various GIS platforms that we have in software, and the initial processing and some of the modeling. So in the lower left, again, a solid model was derived from the point cloud, and this the blue structure was designed in real space again, and spatial constraints and collision detection was run on this, so we could tell a contractor these pieces can come in, you don't have to disassemble them, and these pieces have to be taken apart and broken down, and here's how you assemble it. So, and then on the right is the finished product. So a bit more on the harder. So this is again some asset capture, asset management, as well as monitoring. So this is a bit of an older hydraulic structure that some concerns were brought to light about potentially needing some monitoring. So in the above is a picture of what it looks like. We did a 3D scan on it, derived a 3D point cloud model, and then from that we did analysis on it, and because on a 3D scanning side we're to 2-3 millimeters of accuracy, and we can start performing analysis on the face of that dam, on those, and start monitoring spalling and wear on that concrete face, and then start doing differentials across it and highlighting where it may have worn past maybe a threshold that would be desired. And I'm going to hand it over to Brook.
Next example we have is a train modeling example. So this particular project is of a channel excavation. It's in a remote location that was only accessible by air or boat. So we determined that for this project it would be appropriate to use a photogrammetric UAV to capture the site. It was a very low vegetation site that allowed us to not have to do a lot of point cloud cleaning, as it captured the surface really well. So we were able to generate a digital elevation model from this, and then in turn that DEM was used for quantities. It was also used as a record of the as-built of the channel, and then it was used for hydraulic models to determine future performance of the channel, and also for condition assessment of the slopes of the channel excavation. This next site is a mine site remediation. Several LiDAR flights have been undertaken over various years of the site. It's a fairly large site, so traditional survey methods using GPS weren't really feasible to capture the whole site topography. So LiDAR was flown for multiple years, and digital elevation models were created. It's a mine closure site. So that was the original purpose of gathering the point cloud data, was to generate these digital elevation models. However, because you've got the point cloud data there, even if you're only building a bare earth model and using maybe your ground points from the LiDAR, the other data still exists. So this is an example still at that same site where we were able to use the point cloud data to extract additional information. So there was going to be a road realignment on site, and they wanted to ensure that vehicles were going to be able to safely pass underneath a transmission power lines that were cutting through. So we were able to go in and extract the transmission line data, also having the ground surface to be able to determine if there was going to be enough clearance. Also, because of the LiDAR, we have the date of capture. They were also able to go back from outside sources to determine the temperature and wind, so they could also ensure that there wouldn't be any additional sag on the power lines during different conditions. So that was a really good example of point clouds working in a scenario where you weren't necessarily expecting that application, but being able to use the data to help out a project later on.
So this is the last project example we have, and it's a bit of an interesting one. So this is a project we had up in the Yukon, and this is a historic bridge constructed during the Klondike and the gold rush. So it has cultural and historical significance, and some bank rehabilitation was required on either side of it, and but they wanted to preserve the bridge. So they've asked us to do a 3D scan of the bridge for the purpose of creating an accurate record of it, because the intention was to take it apart, and then once the rehab was done, they wanted to put all that same material back into place. But there was some concern about being able to reconstruct it and it's exactly how it was. So the 3D scan was done very, it was a fairly intense 3D scans. We went around and 3D scanned every element of it so we can document each component of it, and it was used as a record, so when they put it back together, they knew exactly how it would work or go back together. So lastly, so the future of point cloud technology and data and where we kind of see things going. So if you look at the last 10 years, the cost of acquisition keeps dropping, becoming a bit more readily available, affordable, as well as the accuracy is continually increasing, getting better and better. And not only the accuracy, but the resolution. You can now, in 2000, 2002, it was 1 to 2 points per meter, and now we're 30, 40, 50 points per meter, right? So this is the kind of resolutions that can be now attained. Really a lot of this, what's driving this is also the hardware and software on our computers now, and the software can handle these massive point clouds. The one we were just wrapping up, we had up to just under 1 billion points, and we were doing modeling off of that. Drive space now is so much more affordable than it was just a few years ago. So, a few years ago it was gigabytes, now we're terabytes, right? So now it's not unheard of that, most times we're shuffling terabyte drives around, moving these around, and the drive space is not cost prohibitive. So we're seeing monitoring as well as asset capture and asset management. That's a big area that we're going to see probably more and more use of point cloud data, and as well as the ever emerging 3D printing. I think those two we're going to start seeing those going hand in hand now, where a lot of these point clouds and models can be more readily printed, and I think we're going to start seeing these point clouds. I think you're going to start seeing them now being disseminated out through online applications. So just with more and more high-speed internet going in, we're seeing more fiber runs running. So online applications of obtaining point cloud data is, I think you're going to see that more and more. So I guess lastly, is there any questions?
When you're imaging water areas, say flooded areas,
Mm-hmm.
are there any special precautions you need to take so you really get an image of water versus saturated sediment?
it's a good question. So we've got 2 projects that actually address that exact issue. So for instance, you have overland flooding, and so the question is we need to define the effects of that flooding. So that can be defined by standing water, but then soil saturation is also an impact on it, especially with agriculture. So from a LiDAR perspective alone, you're going to get the standing water, but what we've been able to do is from the LiDAR, you end up getting a digital elevation model, and coupled with hydraulic modeling and where the water surface potential is, and as well as following up with some near-infrared for crop stressing, the 2 together, you end up getting coming together what the true effects of where the soil saturation was, as well as the standing water. Oh, sorry.
Can you simulate how water soil you have your LiDAR? So if you manipulate the LiDAR to say that now we're going to behind the scenes add more trees or something, so actually the LiDAR can change, or is it intelligence enough to manipulate? Okay, using as a source of reference.
Right. Yeah, I think I know exactly what you're talking about. So the answer is yes. We've done that a couple of different ways. So for instance, let's say an existing condition, and let's say it was a bank stability, right? So then let's say that there was a bank failure, and you could model what that failure would look like if there's a total bank failure. So you'd model what that would look like, and then you'd superimpose that terrain model onto that LiDAR data to simulate what it would look like if that was a total failure. That's one aspect. The other one that you see more readily is when let's say a highway or a bridge or a building is going to be proposed. So we can do an accurate LiDAR or point cloud capture, and then you can build a 3D object of what that structure would look like. So it'd be an accurate model similar to what that video was that we showed. The other thing that also is some of the historic changes. So let's say if you have for model triangulation from old historic high resolution stereo pairs. So let's say we were going to look at how a river meandered over time. Let's say, so then you could go back, prior to LiDAR data, so what the river looked like and the banks in 1949, 1950, 1960, and then you could look at and compare those models to LiDAR from 2015, 2017 and onwards. So you can actually look at that change detection, and you can actually start modeling and quantifying more readily what those changes of the terrain over time.